Welcome to Lecture 21, and more importantly, welcome to Section 3 of the course. Section 3 is a big topic. It deals with loosely what we call heat, although you'll see that heat is something whose definition in physics is perhaps a little bit different than what you might think. The physics subjects we're dealing with are thermodynamics and statistical mechanics, and they're big enough and important enough that we're going to spend 7 lectures on these subjects that have to do with what, again, we call loosely heat. These are crucial to understanding energy flows throughout the universe, both naturally and technological, in the astrophysical universe, in the geophysical universe. We understand the interior of the Earth, the atmosphere, the oceans, as systems that are ultimately driven by heat. In technology, things like engines and refrigerators are intimately connected with this concept of heat, and even biological systems. I mentioned that we'll be talking about both thermodynamics and statistical mechanics. Why 2 subjects? Because when scientists first started understanding heat and related phenomena, they understood it in kind of a macroscopic view. They didn't understand what was going on at the microscopic level to make these things happen. So that was the subject of thermodynamics, which became fully developed pretty much before people understood the linkage to the microscopic systems underlying it. We will forge that linkage in this course of these 7 lectures, and so you'll understand both thermodynamics, the sort of macroscopic picture, and a little bit of the microscopics. And we'll relate statistical mechanics to Newtonian mechanics, that is, to the mechanics Newton described. Occasionally it needs to be related to quantum mechanics, and we won't go there in this section, but we will understand how thermodynamic phenomena, at least some of them, follow pretty closely from Newton's laws of mechanics. Now, let me begin by talking about the 2 obvious subjects here, heat and temperature. So heat we sort of think of as something. Used to be thought of as an actual fluid. It was called caloric, but it's something. Temperature is a measure of the intensity of whatever that something might be. And a brief history would go something like this. Before 1800, heat was definitely believed to be a fluid. It flowed from hot objects to cooler objects. It was some physical thing that moved. But then in the late 1700s, Benjamin Thompson, who was an American, but was later made Count Rumford of Bavaria, and he went to work as the supervisor of the Bavarian arsenal, and his job was to supervise the boring of cannons. And he noticed that the boring of cannons produces heat, and it seemed to produce an inexhaustible supply of heat. So he concluded that this fluid, caloric, wasn't really a fluid at all, but that heat was something that was associated with doing mechanical work. By the way, Rumford also invented the Rumford fireplace. And then in the 1840s, along came James Joule, for whom the unit of energy, of course, is named, and he quantified that relationship between heat and energy, between calories, which were the measure of heat, and joules, as they became known after Joule's time, which were the measure of mechanical energy. And he made that equivalence, and we'll look at that more later. That equivalence is so direct that in some parts of the world, what we would call a low-calorie soda, for example, is labeled a low-joule soda. So that's just a brief history. And we're going to begin with the easier concept here to understand, and that's the concept of temperature. So let me begin by giving a definition of temperature. First of all, I want to give a definition of what it means for 2 things to be at the same temperature. You put 2 objects in contact so they can exchange heat, whatever that means, and if no macroscopic properties of them change, nothing you can measure about them changes, then they are and were at the same temperature. If some properties change, then they were not at the same temperature, and they will eventually come to the same temperature. You can choose any macroscopic property you want to define temperature. There's nothing magic about alcohol in a tube or mercury in a tube or something. Any macroscopic property will do. You could choose volume, you could choose length, you could choose electrical properties, you could choose properties of radiation, as we'll see. All of these are properties you can use to define temperature. And I want to talk a little bit more detail about how we do that. But before I do, let me show you a couple of thermometers. First of all, I have a rather crude thermometer here that I've constructed by filling a flask with colored liquid. It's just water with food coloring in it, and there's a thin tube extending out of it. You can see the liquid extends upward a ways, and if I put this thermometer in this beaker full of ice water, you can see the fluid level in the tube beginning to drop, and that's happening because the water is getting smaller, its density is increasing, its volume is decreasing as it cools down. This is a lousy thermometer, by the way, because it's so big that it extracts a lot of heat from the system. Well, maybe I shouldn't say heat, but it causes a significant heat flow from the system it's in contact with. It extracts energy from that system, and it actually lowers the system's temperature. If I take that same thermometer and I stick it in this beaker of hot water, you can see that that fluid level begins to rise again as the water expands. Again, a lousy thermometer because it's rapidly cooling down that hot water, and that's not what we would want it to do. This alcohol-based thermometer is, of course, a better realization of that same thermometer with the relatively small bulb that doesn't take a lot of energy from whatever it is you're trying to measure. Here's a dial thermometer. The dial thermometer uses a strip of two different pieces of metal bonded together, and they expand differentially as temperature changes, and that causes a needle on here to rotate. That's a different kind of thermometer. Here is an electronic fever thermometer. It uses the electrical properties of a semiconducting material down in here to measure temperature. And here is an ear thermometer. Stick that thermometer in your ear, and it actually measures radiation emitted by your warm eardrum, and by looking at the profile of that radiation, it comes to a temperature. So all these measure temperature, but they all have to do it by having a common agreement on a standard measure of temperature. And how do we achieve that? Well, I want to do a rather more sophisticated demonstration that shows that. So I'm going to go over here where I have a laptop computer set up, and the laptop computer is displaying on the big screen, and I'm going to do an experiment that will look at temperature and pressure, because one measure we could use, one macroscopic property we could use, is the pressure of a gas at a constant volume. That's a macroscopic property, and as temperature goes up, it turns out pressure goes up. And that, in fact, is one of the best and standard ways of measuring temperature. So let me explain what I have here. I have a hollow sphere, which contains air at, right now, room temperature, but the volume of that sphere is fixed. Attached to it is a little hose that goes into a device that senses both pressure and temperature. In fact, there's also a temperature measure. There's a temperature sensor in there, and this device is picking up both pressure and temperature, converting them to electrical signals, transducers, and sending them into my computer where it will display them. So here's what I'm going to do. I'm going to plunge this thing into an ice water bath, and I'm going to start the computer collecting data. There's the pressure in kilopascals, the red numbers. There's the temperature in degrees Celsius. And as soon as they get fairly stabilized, I'm going to save that measurement in the computer, and the computer will leave a point. There's the point, in fact, where it's going to be. So that isn't changing very much. We've come to a low temperature and a pressure. So we're going to keep that data point. And now I'm going to plunge this same bulb into hot water. It's not boiling, but it's pretty hot. And you can see the pressure and temperature are rapidly rising. There we go. Let it go up a while. 39. We just went through 37 degrees Celsius. That's body temperature. We're going up toward 50. Let's let that go a bit longer. So this process is actually used to define temperature scales. There's a unique temperature that water has at its so-called triple point. And this is the point where liquid water and solid water, ice, and water vapor can all coexist together. And that defines a unique temperature and a unique pressure. So if you get water in those conditions, the conditions of the triple point, the conditions where liquid, solid, and vapor are all existing together, then you know the temperature of the water is exactly, in fact, 273.16 degrees Celsius. That's what defines our temperature scales. Well, we're beginning to converge on maybe something in the low 50s here for the temperature. We don't have to wait till it comes all the way to its equilibrium, because the important thing is that the temperature and pressure in that sphere are related. So we're pretty close, so I'll keep that value also. And now what I want to do is look at an extrapolation. You can see the curve on the big screen. I want to look at an extrapolation downward in temperature from those values. Okay, so let's see what we have. I've fit a line. I've asked the computer to fit a line through those two data points that I got from the hot water and the cold water. And the line is sloping downward. And notice what's happening. We start with pressures around 100 kilopascals, 100,000 pascals. That's typical atmospheric pressure, and we fluctuated between these 2 points. We only had 2 points, relatively closely spaced here in pressure and temperature, the cold point and the hot point. And as we extrapolate that curve downward, let's ask the following question. Let's ask, what would happen when the pressure got all the way to zero? What would happen with zero pressure? That defines a temperature below which we could not go because we can't have pressures below zero. And according to this extrapolation, that temperature is about minus 230 degrees Celsius. In fact, it's telling us right here it's minus 234. And that's not quite the right answer. Measuring two relatively nearby temperatures isn't very effective in getting this extrapolation. But in fact, if you did this experiment more carefully, you would find that the curve of two temperatures with a straight line between them extrapolates to zero pressure at a temperature of minus 273 degrees Celsius. We're not too far off. We're at 234 degrees, minus 234 degrees Celsius. That's the lowest temperature you can possibly go to. That temperature defines absolute zero. So the way really to define a temperature scale is to understand where absolute zero is and say that's the temperature at which one of these constant volume gas thermometers, which is what I have here, would go to zero pressure, and then find some other point, and it's that triple point of water that I mentioned that's actually used to make the definition, and the line defined by those two then defines the temperature scale. So let's look at how we use this idea of absolute zero, this extrapolation using the constant volume gas thermometer to define temperature scales. And what I'm going to show you are several important points in the temperature realm. Absolute zero at the bottom, the temperature at which nitrogen boils, a very low temperature, the temperature at which ice melts, and the temperature at which water boils. The official temperature scale, the official scientific temperature scale, the scale of the SI system, is the so-called Kelvin scale, named after Lord Kelvin. So that's why it's called the Kelvin scale with a capital K. It is a scale which starts out at absolute zero. Its zero is the true absolute zero of temperature, the lowest temperature, that point at which we extrapolated to zero pressure. By the way, a better way of defining absolute zero is it's the temperature at which the energy of a system is the minimum it can possibly be. In classical physics, that would be zero. In quantum physics, there are minimum energies that are not zero, so I have to phrase that a little more carefully. The unit of temperature in the SI system is the Kelvin, lowercase Kelvin, symbol capital K. And if you want to sound sophisticated, don't say degrees Kelvin, say kelvins, because it's a unit just like meters and kilograms and seconds. So I might say, oh, the temperature today is 273 kelvins. I wouldn't say 273 degrees Kelvin. The Kelvin scale is closely related to the Celsius scale. The degree size in the Celsius scale is the same size as a Kelvin. But the 0 point is different. The 0 in Celsius is chosen as being the melting point of ice, and the 100-degree point is the boiling point of water, and that's the scale which extrapolates downward then to minus 273 at absolute zero. So the size of the Celsius degree and the Kelvin are the same, but their 0 points are different. In the United States, we tend to use the Fahrenheit scale, one of the few countries that does, and in the Fahrenheit scale, ice melts at 32 degrees and water boils at 212 degrees. Nitrogen boils down there at minus 321, and absolute zero is 459 point something, about minus 460 degrees below zero, very cold on the Fahrenheit scale. It turns out there are situations where we really need to work in absolute scales, kelvins, where the zero is really absolute zero. Some of the most basic equations of thermodynamics require that. And for engineers working in the United States, there's a fourth scale that you probably haven't heard of and probably won't, and that's called the Rankine scale. And the Rankine scale is to the Fahrenheit scale the way the Kelvin scale is to the Celsius scale. That is, their sizes of a Rankine degree and a Fahrenheit degree are the same, but their 0 points are different, and Rankine is an absolute scale, begins at absolute zero. So a temperature change, let me remind you, of 1 degree Celsius is the same as a temperature change of 1 Kelvin, and that turns out to be equal to 1.8 degrees Fahrenheit, and that's also equal to a temperature change of 1.8 degrees Rankine. So it doesn't matter whether, when you're talking about changes, whether you're saying Celsius or Kelvins, they're interchangeable, and I will do that interchanging quite frequently. So now we've taken care of temperature, but that's really the easiest of the concepts to define. Now let's move on to heat. And I want to talk about heat in some detail. And I want to contrast it with something that is really what you probably think of when you think of heat. So let me define heat. And here's the rigorous definition. Heat is energy being transferred from one object to another as a result of a temperature difference. So the fundamental thing about heat is energy in transit. It's not energy that's inside something. It's a flow of energy. It's not the energy that resides in an object. that energy is called internal energy. So when I have a beaker of hot water, oh, by the way, one problem with my homemade thermometer is it was slow to respond, and it's actually gone and overflowed on us a bit. Anyway, that beaker of hot water, it doesn't contain heat, or more heat than the beaker of cold water. It has more internal energy. And the reason that distinction is important is there are several ways to change the internal energy of a system, and only one of them is a flow of heat. So, for example, if I start with a cold substance and I put a Bunsen burner under it, there will be a heat flow. Because the burner is hotter than the cold thing, there is energy flowing as a result of that temperature difference. That's heat. That's a heat flow. And gradually the object warms up. And when it warms up, I will say about it that it has more internal energy, not that it has more heat. Let me give you some other examples. Suppose I go over here and I grab this can of gasoline. Now, there's a lot of energy in gasoline. And if I carry the gasoline can across the room and put it here, that's a flow of energy, but it is not heat, because it's not a flow driven by a temperature difference. Although I suppose we could argue philosophically, if I was running away from a fire, maybe it is. But that kind of movement of energy is not heat. Neither, surprisingly, is the energy that you put into your food in a microwave oven. You may make the food's temperature go up, you increase its internal energy, but in fact, that energy flow that is delivering energy to your food in a microwave oven is not heat, because it's not driven by a temperature difference. The thing that generates the microwaves is not significantly hotter, and in principle wouldn't have to be hotter at all than the food to which it's supplying energy. It's a different process, raising the internal energy of the water. So heat is something very, very different from what you probably think of. You don't say there's heat in stuff. You say there's internal energy in something. It may have taken a heat flow to get that internal energy there, but it may also not have done that. One other example, back to Count Rumford, drilling his cannons, or you drill into a piece of metal with a dull drill bit and things get hot. That's not an example of heat flow either. Why? Because what's happening there is it's mechanical energy that's making the internal energy change. That was the kind of experiment that Joule ultimately had to do to establish the so-called mechanical equivalent of heat. Now, having said that heat is not something that is in things, I'm going to introduce a concept that is slightly disturbing in that context, because I'm going to use a term that makes it sound like heat is in things. I'm going to define the quantity heat capacity, which is sort of, loosely speaking, a measure of how much heat you can flow into something for a given temperature difference. But the word capacity might sound like the thing is holding heat, and it isn't. Although sometimes people talk that way. Strictly, heat is energy in transit, and it's energy in transit because there's a temperature difference. So let me talk a little bit about heat capacity and a more fundamental quantity, specific heat. The most common result of heat flow is that something's temperature changes. If heat flows into something, the temperature increases. The temperature change, delta T, is proportional to the amount of heat that flowed. Again, once the heat is in there, it's not heat anymore. That proportionality defines a quantity we call the heat capacity. So Q is C times delta T. The heat capacity is a property of a particular object. Its SI units are joules per Kelvin, or equivalently joules per degree C, because the temperature difference doesn't matter whether it's kelvins or degrees Celsius. A more fundamental property of materials is the specific heat C. That's the amount of heat that has to flow into an object for a unit temperature change per unit mass of the object. It's a property of a material, and the formula there is Q is mass times specific heat. That product together is the heat capacity times delta T. And the SI unit is joules per kilogram per Kelvin, or joules per kilogram Kelvin. In other units, it's calories per gram per degree Celsius. Those are two ways of expressing specific heat. And C, this C is the big C, that's the heat capacity, is the product of the mass and the little c. Specific heats of common materials, here they are expressed in joules per kilogram Kelvin, the official SI unit, but commonly also in calories per gram degrees Celsius. And one thing you'll see here is that liquid water has a very, very large specific heat, 4,184 joules per kilogram to raise the temperature by just 1 degree Celsius. Water has a very large specific heat. That's why it's hard to change the temperature of water. And let's move on and do some examples of specific heats of materials and see how that works out. So let's go to our big screen, and look at 3 different examples, one of them really a sort of serious one, and the other 2 kind of interesting and amusing. So let's start out, suppose there's a power failure, and your house temperature drops to 5 degrees Celsius, that's about 41 degrees Fahrenheit. It's pretty cold in there. How long will it take to warm your house to room temperature? 20 degrees Celsius. And I'm going to tell you that your heating system supplies energy at the rate of 30 kilowatts. And it has a furnace or something burning. There is a flow of heat out of it. The house's heat capacity, I'm going to tell you, is 25 megajoules per degree Celsius. That means it takes 25 million joules of energy to raise your house's temperature 1 degree Celsius. Our delta T is from 5 to 20. We want to go up. Q is heat capacity times delta T. That's 25 megajoules per degree Celsius times 15 degrees Celsius. Work it out. We need 375 megajoules of energy. The heat output rate is 30,000 watts. A watt is a joule per second, so that's 30,000 joules per second. So how are we going to find this out? The time will be the total amount of energy we need divided by the rate at which energy is coming in, 375 times 10 to the 6 joules. Forgot the joules there, but there's a joule, and we're dividing by 30,000 joules per second. We get 12,500 seconds, which is about 3.5 hours to bring your house up. Sounds fairly reasonable. Another example, here we are in the kitchen with a stove burner. The burner has an output of 1,500 watts, analogous to the 30 kilowatts of your house. How long will it take to bring 2 kilograms, which is about 2 quarts of water, from temperature it comes out of the faucet, typically 10 degrees Celsius, 50 Fahrenheit, to boiling? We know the specific heat of water is 4184 joules per kilogram per degree C. Delta T, we want to go up 90 degrees Celsius. Q is now MC delta T, 2 kilograms. C, the specific heat, delta T, we need 753,000 joules. We are heating at 1,500 joules per second, 1.5 kilojoules per second. Do the division, takes about 500 seconds or 8 minutes. Reasonable also. Now let's do a more serious example. We got a nuclear accident. We got emergency cooling water dumped into a nuclear reactor. It comes out of the dump tank at 10 degrees Celsius. It's dumped into the reactor. Unfortunately, when you shut down a nuclear reactor, the radioactive decay of its spent fuel is still producing energy at big amounts, in this case 300 megawatts, 300 million watts. How much cooling water is needed if we can keep this thing from boiling for 1 hour so we can take whatever steps are needed to rectify the situation? So we want a delta T again of 90 degrees Celsius. The heat output rate is 300 megawatts, 300 million joules per second. This time we are trying to find out the amount of mass needed. In 1 hour, which is the time we have, we're going to produce 1.1 trillion joules. 300 million joules a second times 3,600 seconds in an hour. Q is MC delta T. Now we can solve for M. This is water. Q, and we do the calculation, and we need 3,000 tons of cooling water. That's a colossal amount of water. Wow. So there are 3 examples using heat capacity and specific heat. Okay, so let's think about what happens if we put a warm object and a cool object in the same vicinity. So here I have, for example, my hot water and my cold water. And in fact, heat is flowing from the hot water to the cold water and warming the cold water. Now, a lot of heat is being lost out into the environment, and heat is flowing in from the environment. So this system is not isolated. But if, as in this picture, I surrounded those 2 things, the hot object and the cold object, with insulation, then the only place energy could go was from the hot object to the cool object, and energy would have to be conserved. Energy couldn't flow out as heat through that insulation. So after a while, they would come to the same temperature, and we want to understand how to calculate what that temperature is. So we can write a statement of energy conservation. Whatever heat flows from 1 to 2, minus that amount of heat flows from 2 to 1. Now, what I mean there is one of those heats is positive and one of those heats is negative. One object loses heat and one object gains heat. That's what's going on. And so if we wrote the mathematics, we're going to say an outflow is negative and an inflow is positive. We would say Q1 plus Q2 is 0. The heat that flows out of the hot object plus the heat that comes into the cold object, being defined as negative, that adds up to 0 if energy is to be conserved. In terms of specific heat, we know the heat flows are given by the masses of these objects times their specific heats times the temperature difference. And so that statement at the bottom of the picture, M1, C1, delta T1, plus M2, C2, delta T2, where the deltas are the changes in temperature of the two objects as they come to some final temperature. That is the equation that's going to characterize the final equilibrium temperature. Let's do an example. So here we are back on our big screen. We're going to be at the blacksmith's. So the blacksmith is going to plunge a 1.2 kilogram iron horseshoe. It's going to be at 650 degrees Celsius, that's about 1200 Fahrenheit, into 6 gallons, about 23 kilograms of water at a temperature of 20 degrees Celsius, room temperature. The final temperature of the water in the horseshoe, what are they? Let's neglect any heat loss to the surroundings. Let's assume this takes place either fast enough or in an insulated container so that there's no heat loss to the surroundings, and we can conclude that energy is conserved. So our energy conservation statement, which we just wrote, is that the mass of the horseshoe times the specific heat of the horseshoe times the temperature change of the horseshoe plus the same thing for the water is 0. Remember, one of these temperatures will go up and one will go down. So one delta T is positive and one is negative. In terms of the final temperature T, the hot object, the temperature, the delta T is the difference between the final temperature and the initial temperature. Same for the water. The difference between the final temperature and the initial temperature. One of those differences is positive. One of those differences is negative. Let's do the math. Solve that whole thing. It's just algebra. Solve for T. We got to multiply through. We got to do some algebra there. But there it is. Do the numbers. We know all the numbers that go into that. And the answer comes out that the water goes up to 27 degrees Celsius. You might say, why only that much? This horseshoe was at 650 degrees Celsius. Well, 2 reasons. One is that we only had 1.2 kilograms of horseshoe, whereas we had 23 kilograms of water. So we had a lot more water. The other reason is water's specific heat is much bigger by a factor of almost 10 than the specific heat of iron. So that's why we have relatively little difference. Okay, well, let's wrap up with a summary here. Heat, we found, is something, or we think of it as something. In fact, what we found it is energy in transit. We have temperature scales that are established by the presence of this temperature called absolute zero, which is the extrapolation downward to zero pressure in a constant volume gas thermometer. Heat, we know, is energy in transit because of a temperature difference, and we contrast that with internal energy, which is what you probably used to think of as heat. Heat capacity and specific heat measure energy needed for a given temperature rise, and substances, if we put them at different temperatures, they come to equilibrium in a way that's governed by energy conservation and their properties like specific heat. Well, let me give you a challenge in case you're interested. Here's the challenge. So let's consider the following situation. Suppose we have a perfectly accurate thermometer, and it has a heat capacity of 65 joules per degree Celsius. And it's initially at room temperature, 20 degrees Celsius, and I'm going to immerse it fully in a liter of water, 1 kilogram of water, at 35.00 degrees Celsius. And I want to ask the question, what does this perfectly accurate thermometer read? And I'd like you to explain your answer. And let me give you a hint. It has something to do with what was bad about that little homemade thermometer over there that I used colored water in. So think about that a moment. Okay, let's look at the solution. The thermometer needs to heat to the final temperature. So heat has to flow from the water, and when that happens, that's going to lower the water's temperature. In my bad thermometer, the amount of heat that had to flow to heat that big bulb of colored water was so big that it really changed the temperature dramatically. The mathematics is exactly as the same as are in at the blacksmith's example. So we'll use the same equation. I won't go through all the math, but there are the numbers that need to go in. And we solve it, and we find out that this perfect thermometer, perfectly accurate, is going to lower the temperature to 34.77 degrees Celsius. And that's what it's going to read. That really is the answer to the temperature, but the temperature has dropped because I put the thermometer in, and the thermometer had to warm up to that temperature. So there's the answer to the challenge.